So before moving to the past paper questions, we have to know what are the important preparations, important chemical reactions, important properties of D block elements. So after discussing about the topics, we will move to the questions. Okay. So first let me introduce the chapter, important topics. I will share my screen. Please let me know if it is visible or not. Okay. So here we are starting from the D and F block elements. So the first one, what are D block elements? So D block elements means they are from starting from group third of the periodic table until 12. They are called D block elements. And the reason is for these elements, the electrons are means the last electron is coming in the d subshell or d orbital. That's why they are called as d block elements. Okay, so this is the definition for d block elements, means the elements from the group third to group 12, and in these elements the electrons will be filling in means the last electrons will be filled in d subshell or d orbital. Now let's see another name of the d block element, that is transition element. Okay, so what is the difference between the why we are calling them as transition element? Means their properties are actually doing the transition from one side to another, right? And we can define the transition element. They are having incompletely filled d orbitals in its ground state or in any one of its oxidation states. This is also important. D block element means we know they are from group 3 to group 12, but coming to the transition element has a different definition. What is that definition? They are having incompletely filled d orbitals. That is important. So if an element is having D10 configuration, they cannot be considered as the transition element. Okay, because for becoming a transition element, D9 is acceptable. Okay, so they should have incompletely filled d orbital or partly filled d orbital. That is, the transition element should have partly filled n-1 d orbital. Okay, so this is how we are defining the transition element. Usually when you come to the some elements such as, for example, zinc. So in case of zinc, I can tell you an example. Zinc has an atomic number of 30 and the electronic configuration will be 3d10 4s2. Okay, so it has 3d10 configuration. So the d subshell is completely filled. So according to this definition, we cannot consider zinc as a transition element, because according to this same definition, we need partly filled d orbital or incompletely filled d orbital. Here 3d subshell is completely filled. It means zinc cannot be considered as a transition element. Okay, now if you consider the common oxidation state of zinc, that is Zn2 plus. Okay, so in case of Zn2 plus as well, it will be 3d10 4s 0. That is, the two electrons will be removed from the 4s orbitals only, not from the 3d. See, even in their means valence state, oxidation state also, the 3d orbitals are completely filled, right? So they are not considered. So that means in ground state or in any one of the oxidation state. Ground state is not only the reason. If they are showing the D10 configuration in its oxidation state also, they cannot be considered as the transition element. Okay, so this is the periodic table. We can see the transition elements are starting from here and they are ending here, right? So we are starting from scandium 21 and that series is ending at zinc. Okay, so similarly we have four series. So we have four different transition series. So the first series is called 3D transition series, because in case of these elements, the 3D orbitals will be filled. And for the second one, it will be 4D transition series, because the 4D electrons will be, 4D subshells will be filled. Okay, so next one is 5D, like that. So based on which orbital is being occupied by the electrons, we can classify the different series, different period of transition elements into 3D, 4D, 5D transition series. Okay, now if you check the F block elements, inside the transition elements or inside the d block elements, we can see another kind of elements. They are inner transition elements. Why they are called inner transition? They are present inside the transition elements. That's why they are called as inner transition element, and they are usually separately placed in the periodic table. Okay, as we all know, they are separately placed and they are called F block elements. So these two separate rows denotes the F block elements. So these F block elements are actually, you can see in the 6th and 7th period. The 6th period is starting from 57 lanthanum. But after that, we are seeing it as 72, right? So 58 to 71 is absent here. It means they are separately placed here. That is 58 cerium to 71 lutetium. They are one kind of F block elements. They are called lanthanides. Okay. Now coming to the next 7th period also, we can see here this is 89 is actinium and 112 is also there. So we have 890 to 103. They are absent, right? So these elements means from 90 to 103, those elements are absent and they are placed separately here. They are also belongs to the F block elements and they can be called as actinides. So after lanthanum, they are lanthanides. After actinium, they are actinides. So this is the classification of D and F block elements. Okay. Now, coming to the electronic configuration of transition metals and their ions. If you consider the 6th and 7th period elements including their F subshell, before that, when we move to the D block elements, we can consider the electronic configuration, that is N-1D NS2 configuration. They all are having the same thing. For example, scandium, that is 3D1 4s2. Right, that is 3D is the N-1D orbital, 4s is the NS orbital. Next, if you are taking iron, it will be 3D6 4s2. This is also N-1 D6 configuration, then NS2 configuration. So commonly we can say transition metals form ions through the loss of NS electrons before the N-1 D electrons. Okay, transition metals from ions through the means they form the ions by losing one from the NS electrons before, because see, while filling the electrons, first the electrons will move to 4s, then only it will come to 3D, because 4s is having less energy than 3D, but still 4s is the valence shell. Okay, still the valence shell is 4s only, but energy difference is slightly different. It is not like our expected thing, like it is 3D has higher value than 4s, but still 4s is the valence shell. It means while removing the electrons, it will move from 4s, not from 3D. After removing from 4s, if we need to remove more electrons, they will come to the 3D subshell. Okay. Now here we can see the electronic configuration of period 4 transition elements, means from 3D transition series. Okay, we can see the transition electronic configuration from scandium to zinc. Okay, so here you can see in case of scandium it is 4s2 3D1, titanium is 4s2 3D2, vanadium is 4s2 3D3. So this is how we are writing. So this electron filling in this, so here the electronic configuration is shown by using the box notation. So when you use the box notation, we have to remember Pauli's exclusion principle, Hund's rule, then Aufbau principle, right? Means the pairing of electrons will take place after each orbital gets singly occupied. That is the first rule. Second one, the electrons will be adding in increasing order of their energy. Third one, if two electrons are present in an orbital, they should be having opposite spin. They are the rules. Now another thing is the electronic configuration of chromium and copper. Okay, so coming back to the electronic configuration of chromium and copper, here we can see different from apart from the other elements, chromium has the electronic configuration 4s1 3d5, because in case of chromium, okay, first we will write the expected one. Okay, so for chromium we are expecting 3d4 4s2, because 24 is the electronic configuration. So till 4s2 it will be 20, then the remaining 4 electrons will come to the 3d orbital. So this is the expected one. Now similarly in copper, till 4s2 it will be 20, then remaining 9 electrons will be in 3d. So this is the expected electronic configuration for chromium and copper, but this is not true because D subshell maximum can accommodate 10 electrons, right? And this 10 is called completely filled electronic configuration. That is D10 configuration is completely filled. Now what is the partially filled D subshell? That will be D5. So if you check the D subshell, the completely filled D10 and the partially filled D5 configurations are highly stable. Okay, so for every element it is like that only, means the partially filled and completely filled configurations will be highly stable. So in case of chromium, if one electron from the 4s is jumping or transferring to 3d, it become 3d5 4s1, right? And if you, in case of copper, if we transfer one electron from 4s to 3d, it become 3d10 4s1. So what is the means what is the benefit of writing this electronic configuration? 3d4 4s2, 3d5 4s1. 3d5 4s1 is more stable because they are having half filled d subshell. Similarly, in case of copper, we can write 3d9 4s2, but 3d10 4s1 is more stable because of this d10 configuration. So that is the electronic configuration of chromium and copper. They have still they are, both of them are having a difference from that of the expected configuration. It is due to the completely filled and half filled stability of D5 and D10 configuration. Now we are moving to the properties of the transition metals. All the transition metals, from the name itself it is clear they are metals, and they are main group elements in each period change from metal to non-metal. Same thing. Now, now coming to the other property, these transition compounds are usually colored. Right, they are always producing colored compounds. And another thing, they are paramagnetic, whereas most main group ionic compounds are colorless and diamagnetic. This is another property. Now the properties of transition metal compounds are related to the electronic configuration of the metal atom or metal ion. Means all this color and properties are completely depending on this electronic configuration only, because based on the 3D subshell configuration only we can predict all the color, magnetic property and everything. Okay, that is also important. Now, what are the properties of D block elements? The first property we can say the atomic size, in terms of atomic size, ionization enthalpy, oxidation state, the formation of colored complexes, their catalytic property, their magnetic property, and formation of the complex compounds. These are the important properties of this D and F block elements. Okay, so first we are moving to the atomic and ionic size. So as we all know, group, the atomic size will increases, and among the period the atomic size will decreases. Same case we can see in case of transition metals as well. Atomic size decreases at first, then remains relatively constant. And say in case of electronegativity and ionization energy, also the same phenomena we can see. Electronegativity and ionization energy is also increase relatively little across the transition metals of a particular period. So these are also important. Okay, please write note down these points. This is very important. Okay, okay. Hope you noted down every points. Next thing is the trends in properties. So along the rows, the nuclear charge is increasing. Why the atomic size is decreasing? Because when we move from left to right, the nuclear charge or number of protons increases, and the D subshell has a shielding effect as well. So the atomic and ionic size remains almost same. So this is also important. Now the radii of the third series are virtually the same as those of the corresponding members of the second series. This is also important. So note down the points. So these transition elements are usually showing the properties, all the kind of properties from ionic size. Now, this is the trend in the atomic properties, including the size, electronegativity, ionization energy, all things. Okay, this is the important part. Now, within the group, okay, so within the group also we can see the trend, that is the atomic size increases from period 4 to 5 but not from period 5 to 6. That is also important. These are the things that we are see here. Okay, now coming to the electronegativity, this also increases within a group from period 4 to 5 and generally remains unchanged from period 5 to 6. Okay, so these points are also important. Now coming to the next one, that is the oxidation states of transition metals. Before that, note down this point. Okay, next is the oxidation states of transition metals. Mainly these transition metals can show multiple oxidation states. That is the important point. Okay. So they are showing variable oxidation states. So this is, and among these oxidation states, plus 2 is the common oxidation state because the ns2 electrons are all, means they are easy to lose, right? But coming to the other oxidation states, they are also possible. But for the elements, there will be a stable oxidation state. So this is an ability of the transition metal to show the variable oxidation states. Okay. So for example, manganese. If you take manganese, they can show plus 2 to plus 7. Okay, that is one important point. They can show from plus 2 to plus 7. Now, if you see this compounds, see when the oxidation state is changing, their color is also changing, right? See, in case of manganese, when they are having plus 2 oxidation state, see the color. When they are in plus 6, this is green color, plus 7 is purple color. See, means this is how they are changing the color depending on their oxidation states. Similarly, if you take some other compounds, oxides of vanadium, if vanadium is in plus 5, this is yellow color, plus 6, orange color, plus 7, purple color. See, so the transition metals can show different color based on the oxidation state. So write down the colors and the oxidation state as well. Okay, hope you are done. Okay, so noted the points, right? Fine. Now, the metallic properties. So coming to the metallic properties, all the transition metals are transition elements are metals, right? And they are having the metallic property. What are the metallic properties? We can see malleability, ductility, then the sonority, all these properties, right? And they are having metallic bonding as well. And coming to the oxides of the metals, we know that metal oxides are usually okay. Yeah. So metal oxides are usually basic in nature, right? Non-metal oxides are acidic. So metal oxides become less basic and more acidic as the oxidation state increases. This is also important. So in the NEET exams, we can expect the questions like this, like there will be some elements. So we have to find out which one is having most basic property, most acidic property. So those kind of things also we have to remember. Okay. Now coming to the color and magnetic behavior, main group anti-compounds are colorless and diamagnetic because the metal ion has no unpaired electrons. See, if the species is not containing any unpaired electrons, they will be diamagnetic, right? But if they are containing at least one unpaired electron, they will be paramagnetic. So based on this thing, we can classify the compounds which is having D0 to D10 configurations into paramagnetic and diamagnetic as well. Okay, so here we can see the some compounds, some salts of these 3D transition series elements. So here we can see all of them are colored, right? From the diagram itself, it is clear they are having different color because of the d block, means partly filled d orbitals. Now coming to the catalytic properties, many of the transition metals or their compounds can be used as a catalyst in many reactions. First example is vanadium pentoxide, V2O5. This vanadium pentoxide is usually used as a catalyst in contact process. What is a contact process? This is the industrial manufacturing of sulfuric acid, right? So in this process, we can use vanadium pentoxide as the catalyst. Now another one, iron. The finely divided iron can be used as a catalyst in Haber process. What is the Haber process? This is industrial preparation of ammonia. So for the Haber process, we can use the iron, and for the contact process, that is the preparation of sulfuric acid, we can use vanadium pentoxide. Now coming to another one, hydrogenation, that is catalytic hydrogenation. We can use nickel. That is, by using this hydrogenation reaction, we can convert the alkenes into alkanes. Okay, so this is another example. Okay, now coming to the cobalt. So cobalt is usually can be used for the synthesis of gasoline. That is another example for the catalytic property. So why they are showing the catalytic property? This is due to the presence of unpaired electrons in their incomplete d orbitals. This is one reason. Another one, they can show variable oxidation states, so they can produce the intermediates in between. That is one more reason for their catalytic property. Now coming to the next one, they are having large surface area because the catalyst, how the catalyst is working, they are providing the surface area for the reaction, right? So they can provide the surface area with free valency. That is also important. Now the magnetic properties can be determined by the DD transition and everything, these kind of things. Okay, now how they are producing the complex compounds. Many complex compounds can be produced from the transition elements, and for example FeCN6, FeCN6 4 minus. So these things you already studied in coordination compounds, right? Because in coordination compounds there is a coordinate bond between the metal ion and the ligands, right? So these kind of complexes are produced by the transition methods. Okay, that is also important. So here we have a few examples for the coordination compounds, and here the metal atoms are also different, and the group or atom which is coordinating with, they are forming coordinate bond with the metal, that is also different. So here NH3 is the ligand, chlorine is the ligand, CN group is the ligand. Okay, so they can produce different coordination compounds. This is the thing. So these are the important topics from the D and F block elements. There we can expect the questions, NEET questions. Okay, so I hope all the points are clear. Now we can go to the questions. Okay, one by one, questions one by one. So you can write down the points, the complex formations and all. So if you are done, just drop a message in the chat box, then I can go to the questions. Okay, hope you are completed. Now we can go to the questions from the past papers. So we can start from the recent past paper 2024. Okay. See, here the question is, the E0 value for Mn3 plus Mn2 plus couple is more positive than that of Cr3 plus Cr2 plus or Fe3 plus Fe2 plus due to the change of which of the reason? Okay, so let us see the E0 value for Mn3 plus Mn2 plus couple is more positive than that of Cr3 plus Cr2 plus or Fe3 plus Fe2 plus. So what is the reason for that? First of all, let us see the manganese, right? So manganese has an atomic number 25 and the electronic configuration is 3d5 4s2. Now if you take Mn3 plus ion, it will be 3d4, right? And similarly, if you take Mn2 plus ion, it will be 3d5 4s0 because two electrons in Mn2 plus two electrons are removing from the last 4s option. In Mn3 plus one more will be from 3d. Okay, so here E0 value is more positive because the 3 Mn2 plus ion has a half-filled structure because 3d5 means it is what? Half-filled electronic configuration, right? So due to this half-filled structure, which results in a substantially larger third ionization energy. Means if you have Mn2 plus ion, in order to convert the Mn2 plus ion to Mn3 plus, you have to remove one more electron, right? So it is not easy to remove one more electron from Mn2 plus. Why? Because Mn2 plus is already stable because of the 3d5 configuration. So no atoms will try to lose their stability, right? So from the 3d5 configuration, they are not ready to change into 3d4. So here the third ionization energy will be very high. Means we have to apply more energy to remove one more electron. So here it will be due to the d5 configuration of this uh, Mn2 plus ion, they are having substantially high third ionization energy. Okay. Now we can say up to D4 means, but the in case of this thing, so here Mn3 plus 2, Mn2 plus 2, Mn3 plus means we are changing from D5 to D4 configuration. Okay, so Mn3 plus 2, Mn2 plus is D4 to D5 configuration. So the reason is option A, that is D4 to D5 configuration. The reason is they are having high stable configuration in Mn2 plus. So we have to apply more third ionization energy to apply to convert it into Mn3 plus. Okay, so this will be the answer. Write down the points to reach out in the answer. Okay, fine, done. Okay, next question. The spin only magnetic moment is same for which of the following ions? Okay. So first one we have to know what is the formula to find out the spin only magnetic moment. Hmm. Okay. What is the spin only magnetic moment? That is, we have the equation to calculate the magnetic moment, that is N multiplies square root of that is the magnetic moment mu is equal to square root of n into n plus 2. This is the equation to find out the spin only magnetic moment, right? So here we have to find out the number of, here n is the number of unpaired electrons. Number of unpaired electrons. Okay, so using the number of unpaired electrons in each of them, we have to calculate which one is having, which of the following are having same value of the magnetic moment, spin only magnetic moment. So first thing we have to calculate the number of unpaired electrons in all of them. First let us consider titanium 3 plus. Usually titanium has atomic number 22, that is 3d2 4s2. We are considering only the valence shells 3d and 4s because all the other shells will be completely occupied. And for predicting the magnetic properties, we have to check the number of unpaired electrons in the 3d orbital. That is also important. Okay, so here all the properties, color, magnetic properties, all the properties are depending on the d subshell and the electrons in d subshell. Okay, so that is happening here. So in case of titanium 3d2 4s2, titanium is 3d to 4s2. When they are converting into titanium 3 plus, they will convert into 3d1 because 2 from 4s, 1 from 3d will be removed, 3d1. So this one electron will be unpaired. So n value will be 1 and we can find the value of magnetic moment, that is square root of 1 into 1 plus 2, that is square root of 2 only. Similarly, next we can find out in case of Cr2 plus. Chromium has an atomic number 24, that is 3d5 4s1. Now chromium 2 plus means it will be 3d4. So all the 4 electrons will be unpaired because 5 orbitals are there in the d orbital, right? D subshell, right? So n equal to 4 and we can write the value of mu will be square root of 4 into 4 plus 2. 4 plus 2 means 6. So 4 into 6, that is square root of 24. Now coming to Mn2 plus. Mn2 plus is having 3D, manganese is having 3D5 4s2. So when they are converting into Mn2 plus, they will convert into 3d5 for a 0. Here all the 5 electrons in the 3d orbital will be unpaired. So n equal to 5. So the value of mu will be square root of 5 into 5 plus 2 is 7. Square root of 35. Okay. Now coming to Fe2 plus. Iron is 3d6, 4s2, and when they are converting into Fe2 plus, it becomes 3d6 only. So 6 means the first electron will be paired and there will be 4 unpaired electrons, right? So we can write mu value will be equal to 4 into 6, that is square root of 24. This value is similar to that of Cr2 plus. Okay. Now if you check it out, it is for scandium. Scandium is 3d1, 4s2, and scandium 3 plus means it is 0 only. So number of unpaired electrons equal to 0. So the magnetic moment value will be also 0. So here which of them are having similar value? That is only for chromium and Fe2 plus, that is square root of 24. So which are the answers? Option B and D are having same value. B and D is coming in option C. So which is the correct answer for this question? Okay. So calculate all these values, then only you will get the answer. Write it down. Yeah, you have to calculate all the values for each of the, means calculate means we have to check for each and every ion is given here. Then only you can find out which of them are having same values. So write down everything. Completed? Okay. So this is a big question, but don't waste more time on this because we have less time for every question. So, okay, we have to finish 50 questions in chemistry, then 50 in maths, physics, then 100 questions in biology as well. So don't waste more time. Okay, done, right? Okay. Now the next question. During the preparation of more salt solution, which of the following acid is added to prevent the hydrolysis of Fe2 plus ion? Okay. So during the preparation of more salt solution, so that is more salt is ferrous ammonium sulfate, right? So which is the reactant that you are adding here? That is sulfuric acid. But not only sulfuric acid, it should be dilute sulfuric acid, because if you, we have to make the medium acidic, right? If you are using concentrated sulfuric acid, we cannot use that because this reaction will be interfered. Similarly, if you use hydrochloric acid, nitric acid, any other acids to make the medium acidic as well, it will not give the proper result. So the reagent should be dilute sulfuric acid. Option B is the correct answer. Okay. Okay. The next question. The pair of lanthanide ions which are diamagnetic. So here we have different pairs of lanthanide ions. We have to choose the pair which are diamagnetic in nature. The first option is gadolinium 3 plus and europium 3 plus. Okay, first one we have to know what is the what is the criteria for diamagnetism? Diamagnetism means the compound should contain at least means they should contain all the paired electrons. If they are having unpaired electrons, that cannot be, that will be paramagnetic in nature. Okay, so we have to know that the one which is having unpaired the paired electrons, or which of them are having F0 configuration, F14 configuration, they can be considered as the diamagnetic compounds. Okay. What is Bayer's reagent? Okay. So we have to know what are Bayer's reagents. So first of all, we have to know what is the use of Bayer's reagent. So the Bayer's reagents are widely used in means it is used as a qualitative test for the presence of unsaturation, means to check the presence of double or triple bond in an organic compound. So this is actually an alkaline solution of cold dilute potassium permanganate, that is KDPO. MnO4. Okay, it is a alkaline solution of cold dilute potassium permanganate. So this is usually used to identify the presence of unsaturation, that is double or triple bond in the compound. Means when these alkenes or alkynes containing the unsaturated bonds react with the base reagent, the purple color, usually potassium permanganate is purple color, right? So when they react with these unsaturated compounds, the purple color of the compound will disappear. And as a result, they will produce a brown precipitate of manganese dioxide as well. So this is the reaction, means KMnO4 is losing their purple color and they are converting into a precipitate of manganese dioxide. If there is no any unsaturation, the solution will remain purple, means KMnO4 cannot be converted to MnO2. So this is the test to identify the presence of unsaturation. If the compound is unsaturated, the purple color will disappear, and the result of the reaction will be the precipitate of manganese dioxide with the brown color. If it is in a saturated hydrocarbon, an alkane, the reaction will not take place and potassium permanganate will remain unchanged. Okay, so from these options we can say the correct answer, that is the potassium permanganate. Potassium permanganate means, I told you, it is a cold dilute aqueous solution. So first one is acidic potassium permanganate solution. So this is not the correct answer. Now because they are not acidic, they are aqueous solutions only. Okay. Second one is acidic potassium dichromate. Dichromate is not Bayer's reagent, that is again incorrect. Third option is cold dilute aqueous solution of potassium permanganate, which is the correct answer. And last one is also correct because incorrect because it is given as hot. So it should be cold and aqueous solution of potassium permanganate only. Okay, so C is the correct answer. Done, right? Okay, coming to the next question. Here, which of the following pair of ions will have same spin only magnetic moment values within the pair? Okay, this is similar to that of the previous question, right? So we can calculate the spin only magnetic moment using the equation n into n plus 2 to the rise to 1 by 2, means square root of n times n plus 2. N is the unpaired electron. So if you calculate by using this equation, I'm not calculating for everything because you can calculate by using the same method as we discussed previously. Okay. So if you do that, I will write the values here. For Zn2 plus ion, you will get the value 0. And for titanium 2 plus ion, you will get the value square root of 8, because here in case of zinc n is 0 and here it is n is equal to 2. And for chromium 2 plus, you will get square root of 24 because the number of unpaired electrons will be 4. This already we calculated, right? Okay. So next is Fe2 plus, you will get square root of 24 again because n equal to 4 only here also. Okay, now coming to the next one is titanium 3 plus, we will get a value of square root of 3 because n equal to 1. Okay, now coming to Cu2 plus, copper 2 plus ion, here you will get a value root 3, again we have n equal to 1. Next is vanadium 2 plus, square root of 3, sorry, square root of 15. Okay, square root of 15 because n value is 3. Now last one, Cu plus ion 0 because n equal to 0. So these are the values that you will get if you calculate. Okay, so from this we can conclude that the same number of unpaired electrons in Zn2 plus and titanium 2 plus, no, they are 0 and square root of 8. Cr3 plus Fe2 plus, yes, this is the correct one. They are having same value. Now Ta3 plus Cu2 plus, yes, square root of 3 because n equal to 1. Then vanadium Cu, they are also not having the values. So the correct answers are for the pair B and pair C. We have similar values for their Means for pair B, Cr2 plus Fe2 plus is having same value, that is square root of 24. And for titanium 3 plus Cu2 plus also having same value, square root of 3. So these two pairs are having similar values with each other. So the correct answer is B and C, that is option D is the correct answer. Okay? D. Then, okay, I'm giving you extra time to write the points, so don't waste the time, write down everything properly, okay? Yes. Next question. We have two list here, list 1 and list 2. We have to match these two lists, list 1 with list 2. So the first one we can see lanthanide. Which among the following is a lanthanide? Okay. So among these four, cesium, arsenic, cerium, arsenic, cesium, manganese. So from these four, lanthanide is the cesium, right? That is always confirmed. Now coming to the D block element. D block element will be manganese. So this is A and D block element is manganese, that is B. Now coming to the P block element. P block element we have S and Cs. Which among the following is the P block element? That is arsenic, right? So this is C. Now cesium. Cesium is the S block element. D. So it will be ACDB. So for first one, cerium. Okay. Then D block element is, yeah, manganese. Then P block element, yes. Then S block element, yeah, fine. So this is the correct classification. Fine. The simple question, right? Yeah. Now, the next one. The oxidation states not shown by manganese in given reaction is what? First of all, we have to find out the oxidation state. Manganese is a transition element, right? They can show variable oxidation states. So here first we have to find out the element manganese, oxidation state of manganese. So first let us consider MnO4 2 minus. MnO4 2 minus. First listen, okay? So manganese has an oxidation number. I'm taking it as X, and oxygen always minus 2. So according to the rules to find out the oxidation number, the summation of the oxidation states will be equal to the total charge of the species. Here the charge is minus 2 only, right? So we can write X plus 4 times minus 2 is equal to minus 2. Because charge is minus 2 here. Now 4 oxygens are there. So the total charge of oxygen is 4 times minus 2. So X minus 8 is equal to minus 2. X minus 8 is equal to minus 2. Then X we can write minus 2 plus 8, that is plus 6. Means here the oxidation state of manganese is plus 6. Now which is the compound? MnO4 minus, right? So in MnO4 minus we need to find out. Same, I'm taking the manganese as X, oxygen is minus 2, and overall charge of the compound is minus 1. So X plus 4 times minus 2 is equal to minus 1. So X minus 8 is equal to minus 1. Then X equal to plus 7. So plus 7 is the oxidation state of manganese in one of the product. Now we have one more product, MnO2. MnO2. I'm taking manganese as X. So X plus 2 into minus 2, because we have only 2 oxygens, that is equal to 0 here, because MnO2 is a neutral species. Before MnO4 2 minus, MnO4 minus, they had the charges minus 2 and minus 1, but MnO2 is a neutral species, so we can write X minus 4 is equal to 0. So X will be equal to plus 4. So in MnO4 2 minus manganese is plus 6, MnO4 minus manganese is plus 7, MnO2 manganese is plus 4. So plus, we have to find out the one oxidation not shown by manganese. So plus 6 is shown by manganese, then plus 4 is shown by manganese, plus 7 is also shown by manganese. So the one which is not shown by manganese is B and E, that is plus 2 and plus 3. So So option D will be the correct answer. Okay, write it down. Next question. Which of the following statements is correct? So we have four different statements here. We have to choose the correct one. Okay. So let us see each and every options given here. The first one is magnesium plays role in neuromuscular function and interneuronal transmission. Both intraneuronal transmission and neuromuscular function depending on calcium, not magnesium. So here option A is incorrect because magnesium is not playing the role. Calcium is the one which determines this role. Okay. And coming to the option B, the daily requirement of magnesium and calcium in human body is estimated to be zero point 0.2 to 0.3 grams. This is the correct statement. Okay. This is the correct because about 200 to 300 milligrams of calcium and magnesium are required by our body in each day. So this is the correct one. If you check other options, in C, it is given all enzymes that utilize ATP in phosphate transfer, it requires calcium as the cofactor. This is also incorrect because every enzyme that uses ATP for phosphate transfer needs magnesium as the cofactor, not calcium. So C is about magnesium, not calcium. So this is an incorrect statement. Now the last option, the bond in human body is an inert and unchanging substance. This is also incorrect because in human body the bond is not an inert and unchanging substance, right? So this is also incorrect. So the correct answer is B. Okay, done. Next question. The stability of CO2 plus is more than CO plus salts in aqueous solution due to which of the following reasons? Okay. First of all, let us define the given terms. Ionization energy. Ionization energy is the amount of energy required to remove the loosely bounded outermost electron in an atom in the isolated gaseous state of the atom, right? So second ionization energy means this is the amount of energy required to remove the second outermost electron. First ionization energy is the energy required to remove the first outermost electron. Now coming to the enthalpy of atomization, this is the amount of energy required to atomize. Means if you want to convert the molecule into atoms, we have to apply some energy. We have to break the bonds between them, right? So those amount of energy that we require to break the bonds in a molecule to convert them into atoms, that is called enthalpy of atomization. Now coming to hydration energy, this is the amount of energy change when a particular ion gets hydrated. That is hydration energy. That all we know, right? So because of which of the reason the stability of Cu2 plus is more than Cu plus? That is the question. So Cu2 plus is more stable than Cu plus because of the hydration energy. Because the hydration energy is more negative for Cu2 plus ion and it is comparatively less for Cu plus ion. So this more than make up for second ionization enthalpy of copper. Okay, so hydration energy is the correct answer. Next question. Gadolinium has a low value of third ionization enthalpy because of which of the reason? Okay, so usually gadolinium has the electronic configuration that is equal to the electronic configuration of xenon, then 4s7, 5d1, 6s2. This is the electronic configuration for gadolinium, right? So after the removal of third electron in gadolinium, it will be removed from 5d and 6s. So gadolinium 3 plus ion will be equal to the electronic configuration of xenon, then 4f7, right? This is the electronic configuration. So after removing the 3 electrons for C, third ionization energy is the amount of energy required to remove the third electron. After removing the third electron, gadolinium will be converting into xenon 4f7 configuration. So this 4f7 means it is half filled because f14 is the maximum capacity. So f7 means it is a half filled configuration. Okay, so they are highly stable. As a result, we can say the third ionization energy will be less because the gadolinium can easily produce the gadolinium 3 plus ion. Why they are producing easily the the 3 plus ion? Because when they produce the 3 plus ion, they will be highly stable. So they need only less amount of energy. Okay, so here the less ionization energy, it means they have the exchange enthalpy that is very high. Less ionization enthalpy means they have high exchange enthalpy. So the correct answer is option A. Okay. Write down the electronic configuration, then write the reason. So this is all about the listen questions from the chapter. Now, in the next class, we will meet with one more chapter. So that's it. Okay. So thank you. Signing off. Bye. Good night.